Hello, everyone. My name is John Zuho, I'll be moderating this first session before the break. Our first talk of the morning is from Matt Turk on the current state of YT visualization. So go ahead and take it away, Matt.
Sounds good. All right. Hi, everyone. Thanks for coming. I'm going to give a short talk about the state of visualization in YT, and I look forward to being interrupted when it's 5 minutes left. I'm going to keep the chat window open, and I want to start out just by saying hello. Thank you all for coming. I also want to take a minute just to say how grateful I am to have this opportunity to share with you, to see the other talks and the research that folks will be sharing. And I want to say that I'm really grateful that we all have the ability to be here and to be, present, as it were, for this experience. And a lot of that is thanks to the incredible organization that Stephanie has done, as well as the folks at the Simon Center. So thank you. So I want to start out with a statement about what I think YT is, and that's that YT, in my opinion, is less of a visualization engine than it is a set of components that are in general tightly coupled rather than loosely coupled, but coupled components to construct the inputs to visualization engines. So I want to start out with an ontology of visualizations, and this is something that Ryan Wyatt from the Morrison Planetarium at the Cal Academy of Sciences said at a talk 15 years ago or something that really stuck with me, that there are visualizations that we make for ourselves, and these we can think of as our excellent adventure, our adventure through things, our visualizations that we make for our peers, and this is where we potentially put these visualizations in front of other people. These we can think of in some ways as our bogus journey. This is where we see what may be falling short with our visualizations, and the visualizations that we make for everyone else, not just our peers, but potentially for the public. And in this case, this is really when we have to face the music, if you will, the visualizations that we make for everyone else. And so each of these types of visualizations, each category brings with it different needs for the narrative that is embedded or surrounds the visualizations, the interactivity that we might expect or that the viewers might expect, for our control over the different aspects of the visualizations, and for the visual language that we use to convey information. I'm not going to talk as much about the visual language specifically, but one thing that I want you to think about is how do we keep in mind is that we embed in the way that we present things a number of different assumptions. We use a consistent visual language that says things like this pixel refers to this spatial extent, or these fields are continuous, or things like that. So I want to continue. I can't keep saying that I want to start with something when I've already started several times. Continue by looking at some of the most common things that we do in YT. And the first one that, and I'll note that Sam Walkow is going to be giving a talk later this week, and she's done a lot of information science type studies around the data storytelling that people use when they explore data. When we see the data. So this snippet of code right here, ds equals yt load sample, p is equal to ds.r : integrate density along the axis of z, and then plot. This is a way of seeing our data. And it generates for us a visualization like this, right? It's got our x-axis here, our y-axis here, z is the direction along which we integrated, and then it's got some field, right? But what's actually happening on the back end when we do this? There are a number of different steps that are wrapped into this that we don't necessarily see. The first step, which in this case is sort of a null operation, but that's that data is selected. So we choose, yes, isolated galaxy is so lonely. We choose the data, and in this case, that takes place right here, where we say, give me all of the data. The index is collapsed into a quad tree. I'm not going to go into that in too much detail, but it's important to note that we construct a reduced data object from our full data object. The data is loaded chunk by chunk and then applied to that quad tree, integrating the path length along each component in the variable resolution regions. And then the quad tree is used to create a two-dimensional data value buffer, not a set of uint8s or anything like that, but a data value buffer. So values that are like 10 to the minus 3, in different areas that are two-dimensional, that are regular in size, that then get supplied to Matplotlib. Matplotlib then takes it away from there. It does things like the normalization process. It applies a color map, in this case, the color map Arbra, and it sets up all the different pixels that get blasted out to a screen, saved to a PNG. Let's say that we were to zoom in by a factor of 10 on that plot. We zoom in, but the thing is that because of how we've structured the data ingestion earlier, different things happen. We no longer need to select the data because we already start with our quad tree, so we don't need to collapse into that. We don't need to load any more data because we're storing an intermediate data product. Our quad tree is then used to create a new two-dimensional data value buffer, which is then passed back to Matplotlib. So in this step, this is nigh instantaneous because all we have to do is repixelize. We still, generate a whole bunch of pixels, but the process of pixelization of generating this two-dimensional data value buffer goes a lot faster. Now, you might say, all right, well, let's not do things in a spatial sense. So we can do something like ds equals yt.load sample isolated galaxy. And then we select data. In this case, I'm selecting from 0.4 megaparsecs to 0.6 megaparsecs along the first dimension. And then just take everything along the x or the y and the z dimensions. Then we can profile it where we specify new sets of dimensions, in this case, density and temperature, and a cell mass will be our color. And let's not weight our field, and then we plot it. So again, what is actually happening in this case? The data is selected. In this case, it's a rectangular prism that's 2 megaparsecs along one of the dimensions. The bounds of the resultant profile are computed. And when I was writing this slide, I actually came up with a fun idea for a hack week thing, or a busy week, or whatever we want to call it. The data is then loaded. It's iterated over individual chunks. It's identified as to which bounds it falls into in the density and temperature. It implicitly generates a cell mass field, which is a combination of density and the cell volume, and the cell volume comes directly from the index. Then finally, the bins and the bounds are passed to Matplotlib as a two-dimensional data value buffer. Now, inherently, this is a much more lossy process. We lose more information than we do from our projection plot. So if we were to change the bounds here, we actually would need to make a second pass over the data. But let's take a step back. So this is what YT does from a very pragmatic perspective. But is it possible that we could apply a set of categories of operations to this? And again, be sure to come to Sam Walkow's talk. I think that it is, and I'm going to talk about how that informs our process of visualization. So basically what we're doing is we're talking about taking a set of data and registering it along different dimensions, in most cases spatial dimensions, but in some cases non-spatial dimensions. But these dimensions have to be continuous, and we typically have to define a metric of distance for them. We can apply transformations, we can apply selection operations, and we can apply reduction operations. So for instance, with a registration operation, in particular with the data set that I just showed, it's an adaptive mesh refinement data set that is stored in multiple HDF5 files on disk. Perhaps it's laid out in some way that may or may not correspond to the spatial organization or the physical meaning of what the data represents. So we then have to ingest it into memory in some manner that presents itself as possible to organize, in a logical structure. So we might load it in and have different pointers between different regions and whatever. And then finally, and in this case, it was a Cartesian data set, but it may not necessarily be a Cartesian data set. What we want to do is we want to take that logical structuring and then order it or construct it in such a way that we have a definitional mapping between a spatial location and a value for a field. So the fundamental operation that we want here is f of x, where x is a vector. We can, of course, do this with particles too. I'm not going to talk about the particle support in YT4 just yet, but in this case, the functional form can, be a little bit more expensive, where typically we have to do things like integrate over a set of neighbors or something in order to compute the value at any given point. So we can also apply transformations to our data sets. Typically, we store on disk things that are primitive variables, so things like rho, velocity, energy. But the thing is that this does not describe the entire set of fields that are in our data set, that describes the set of fields that are stored in the data set, but not necessarily the full set of information that can be generated from those fields. So as an example, here's our isolated galaxy data set, and we can look at, say, the velocity in the x direction and the y direction. And as long as we have some type of a spatial registration for our field, we can do combinations of our fields at every single location. So for instance, we can take our two velocity fields in the x and y and use them to generate a field that exists only in potentia. So for instance, the velocity magnitude. So this is also how we do things like generate cell mass, how we generate the molecular hydrogen fraction. That's a verbal tick of mine. I always go back to molecular hydrogen fraction. How we can generate all these different pieces of information that fully describe our region, even if they are not necessarily the most primitive representations of that description. We can also apply selections. So for instance, we could have our fun AMR data set here where we have multiple different regions, and we can select things based on some sort of a spatial extent. We could, in principle, also select things based on other extents and use that as input into our subsequent reduction and visualization operations. We can also apply reductions. So this is one that I'm not going to talk about, but we've done some work with integrations along paths. But this is also what we see whenever we do a volume rendering, where you have some type of a path that is described in a functional form that moves through an object, and then there's an accumulation step that happens as each ray marches through your volume and accumulates different objects or different values. And then finally, what we do with visualization is we take all of our different operations, our registration, our transformation, our reductions, and then we compose them in different ways. So for instance, this is a Ramses data set, and perhaps it's laid out on disk this way. We apply a registration step to it, which implies that we are assigning each data value to a spatial location with some type of an extent, some type of set of values. Once we have fully registered our data set so that we can query any individual point, we can then do data reduction operations. Like, for instance, we could search for halos in our data set. And then once we have those halos, they are now they each have affiliated values with them. We can then construct from that some type of a representation that applies a model that applies to them some type of meaning that we can infer scientific principles from. Okay, so whatever, Matt. You're probably thinking this looks a lot different than what I usually do with YT. And you're right. Okay, we don't necessarily think about stuff from this perspective. Yeah, we're probably all using derived fields. We're probably doing selections like spheres, but this is a rather highfalutin way of thinking about the process of visualization when we really just want to know how galaxies form, or how supercells form over the plains in Middle America. So let's think again about who we aim our three types of visualization at. We aim it at ourselves. We aim it at our peers, and we aim it at everybody else. And I would argue that at present, YT naturally encourages us to think far too often about visualizations for our peers at the expense of visualizations for ourselves. And this is a funny way to describe this, because the very first thing that people typically do with YT when they are looking at a new data set is they generate a plot that spends a fair bit of time making itself ready for publication. And usually we do that through a plot window. The plot window object does so much. And it does it all really well, at least in my opinion. I am not responsible for the code in Plot Windo. It does it really well, and it does it really thoughtfully. It manages a large amount of state. It manages what to do when you move the viewport. It manages the labels on your axes and your units. It manages data-centric annotations on your plot. It handles things like log, non-log, I don't know why I put unlog in there, the buffer size, the dots per inch. It manages a ton of stuff, and nearly all of it directly interfaces with Matplotlib. And I want to note that even though while it uses Matplotlib, and in some cases, and for the Plot Windo object specifically, it exclusively uses Matplotlib, that does not make it redundant with Matplotlib. And this is a really important distinction. We overlap without redundancy in most cases. Matplotlib is a visualization engine that provides many things that YT utilizes under the hood, and some things that YT does not. I'll give a quick example of that. Matplotlib has a really cool set of axes transformations and projections, and in general, YT doesn't use them that much. And that's something that maybe we should think about. YT presents a largely stateful approach to our plots, where our state is roughly divided into two categories. State that's guided by the data or the metadata of the field, the data set, or some collection of those things that's being, or collection being visualization, visualized. And then state that is guided by explicit wrappers around that Matplotlib functionality, like take log, setting the log of a field, for instance. That's something that Matplotlib manages, but YT also presents an interface to it. And I also want to take a side note that it's really trendy in some circles to take cheap shots at Matplotlib, and I really think that's unfair and bad form. And so that's my straw person argument for the day. So let's talk about overlapping redundantly. So on the other hand, perhaps the argument could be made that Plot Windo does too much, that it manages two different things. And maybe it's too tricky to get at the raw buffers, like if you want to set up a complicated multiplot or something like that. For things like slices, it's not too hard to get around that. We can use our handy dandy R notation here. So I can say R : 1024J, comma, : 1024J, comma, 0.5, and then ask for density. And this means set up a pixel buffer, or a data value buffer that has 1024 on one side, 1024 on the Y side, and is sliced through the domain at a coordinate of 0.5, and give me the density values there. This actually returns to you a two-dimensional array. For projections, it's a bit trickier. You have to call this toFRB function. And I mean, FRB, that's this weird term of art that nobody's heard before. There are other types of viz as well, though. For instance, we talked about our excellent adventure, our ability to explore data. So if you wanted to interactively explore a projection plot, we have methods for doing that. You can, of course, use the API. We can call pan_rel. And in this case, what that does is it means pan relative 0.1, 0.1. This means pan by 10% in the X and the Y directions. It's relative, so you can use it to say, move your window a little bit, and then it spits this back out for you. And you'll see that, yeah, the center of the galaxy moved by like 10%. Wow, okay. And the best thing about this is that it's definitely not cumbersome in any way. And Matplotlib is definitely the only visualization engine out there, and it's also suitable for all possible circumstances, right? Right? Okay, I'll tone it down a little bit, and I will just be excellent to each other. So let's talk I'm going to talk a little bit about ideas for how we can make this better, specifically in service of exploratory visualization, okay? The visualizations that we construct for ourselves. So I think that what we could do is we could talk about how to make it easier to get YT out of your way. I'll explain what I mean by that in just a minute. We could build out exploratory methods and widgets. And we can also work on supplying data to exploratory tools. And this would be interfacing with the broader ecosystem that's out there. And there is a gigantic ecosystem out there. So I'm going to talk about two in whatever time I have left. I imagine I have like 3 minutes left. John, do you happen to know how much time I have left?
You have, I'm about to tell you that you actually have 10 minutes from now left.
Nice.
Because we started
Awesome.
5 minutes late. So.
Oh, okay. So I'm going to talk about two different projects that we've been working on at well, not just here, but that we've been working on a little bit. The first one is called widgets, and that's not a typo. You know, it's pretty clever, right? Having the YT in there. Madiq Monk and I started working on a project called widgets a couple years ago. And it started with the thought, what if we invested some time in pushing data to the client in order to improve interactivity? And I'll explain more what I mean by that right here. When we call panrel, if we're in, say, a Jupyter notebook, and a lot of people are in Jupyter notebooks, but not everybody is, this calls back to Python. Python then calls a bunch of different routines, whatever, and then it takes this PNG image, and I think it converts it to base 64. It might send the raw binary, I'm not sure, but it then passes it back up to the notebook. And so there's a series of sets of latency that happen there. There's the latency for you to type panrel, for that message to get sent, for things to happen over here, for a connection to be initiated and then received, and then for it to be added back into the document object model in your web browser. Now, mind you, when I was doing my thesis work, I remember basically we had tilde/public_HTML, and I would just output tens of thousands of PNG files into public HTML, and then I would visit that from my web browser. But that was way before Jupyter Notebook. So widgets, though, it's a pretty fun project that we've been working on. And it has a couple different components to it. And the first one that I want to show is the idea that we have a pan and zoom interactive widget. It was in like 2005 that the Slippy map was first deployed on Google Maps, where you can touch something to move it. You can click and move. I lost my train of thought. And oh, it's been a dream of mine to have that with YT. And we tried a couple different ways of doing this. For instance, with what we called the map server, where you could just spin it up and it would show a map, and you could click and drag, and it would dynamically generate new tiles. But a couple years ago, Madiq and I were looking at the idea of pushing as much computation to the client as possible, because we can't always rely on a server to have to be accessible, for it to work, for it even to exist. But we can always rely on the client being there. And so we started porting a couple of the routines underlying the YT visualization system to a language called Rust. And then we used a compiler toolchain to convert these into something called WebAssembly. And so what WebAssembly is, and if you've ever played retro games at the Internet Archive, you have used WebAssembly. WebAssembly is a reduced instruction set that can run inside the sandboxed environment of your web browser, and it runs at near native speeds. So instead of running JavaScript, it's actually running things inside a WebAssembly virtual processor, and it runs things very low level, and it's pretty fast. So what we're doing here is we say YT load sample, and then we call s.display, because I've imported widgets up here, and we've monkey patched our slice object to have a display method, and we call .ss. You'll see now we've got a couple widgets here that describe it. So let's log our color scale. And we've got our navigation, so we can zoom in and out, but we've also got, oops, I zoomed too far in. We've also got a Slippy map here. And so what's happening as I click and drag, no data is being sent back and forth between my browser and the Jupyter Notebook server. So this could be running anywhere. Yeah, 5 minutes for real?
5 minutes.
Okay.
Yeah.
It's all running inside the client. And so now we can actually interactively explore. And we have a lot more to add to this, but we're working on it. We've also worked a little bit on what we're calling a dataset viewer. So particularly for AMR grids, it's useful to be able to see the positions inside the domain and be able to see how we generate different different values. And so for instance, maybe you want to look at the different fields that are accessible inside it and understand how the fields are generated. So for instance, the disk angle, oh, it's generated via deprecation. Or maybe you want to look at a set of parameters for your data set. And so on and so forth. And we're working to tie all of this together. And so that's the first of these projects. The second, oh, I should have changed to that slide. The second project, which we call YTIDV, we rejected the name Kaival Ren after the atrocity that was Rise of Skywalker, was started by an undergraduate student at University of Illinois named Chuck Rojan many years ago. And it kind of stopped for a while after he graduated. And then a couple years ago, I started fiddling with it, and then Chris Havlin and I started digging deeper in the summer, and now it kind of works. And what YTIDV is, and I realize now that I did not set up my demo for this. What YTIDV does is a full OpenGL volume rendering system with lots of different annotations and so on, and it's all governed by traitlets. And I really wish that I had opened up my notebook here. Oops. So it has state management governed by the same thing that manages widgets inside Jupyter notebooks and so on. And it's got a fun little interactive GUI, whatever. Sometimes it doesn't update right away. But the idea behind this, oh yeah, I use i3. The idea behind this is to take a bunch of functionality that is exposed inside YT and then to put it inside a different method for visualization, to swap out the visualization engine. And in this case, I don't have this demo ready, unfortunately, but this one even ties back into this, and I'm really regretting, I'll probably show it later, where you can use this to control the camera and then do off-screen volume rendering. So for instance, you can log into a supercomputer machine and then execute off-screen volume rendering using the scripting system at hardware speeds instead of software speeds. Chris has been working a fair bit on getting the transfer functions nice and all that. But both of these are projects that we're working on, trying to expose more visualization in YT by making it easier to get YT out of your way and to supplement with some exploratory methods and widgets. And ultimately, we want to make it so that we don't necessarily have to implement all these things. And that was what we were aiming for with this. We were aiming for not having to implement everything. And you'll note that we're relying on lots and lots of different tools. So at this point, I want to just have a last minute thought on state management. A lot of code in YT would be simplified if we started thinking about objects as explicitly stateful with well-defined transitions between states. And come to my lightning talk about declarative analysis. I was told that I had to give a lightning talk, so I will be giving a lightning talk. They told me they were going to say that they forced me into it, but I guess they haven't yet. Thank you again, everyone, for coming. I will go ahead and answer the question that Corentin put in there. IDV for non-patch-based grid datasets is not yet working. However, I am working on particles. I just got geometry shaders in there. I also find this stuff really fun. It would have, so I've been exploring with that, and I totally want to connect on beyond the grid stuff. So, thank you, everyone. And I don't know if there's time for questions or not.
Yes, there is. We have 5 minutes for questions. Thank you, Matt. So if you want to ask a question, use the raise hand feature in Zoom. So if you open up the participants list and just hit the raise hand button and I will call on you. Okay, Madikin.
Hey, Matt, I love the talk. Can you tell me what you made your animations in earlier in the talk? Because I think they were really beautiful and I think all of us would like to use them.
So those were all done with D3. So Jill Naiman and I have developed a course at U of I on data visualization, which has really expanded my horizon of data visualization tools. And I taught myself D3 by making these visualizations about a year ago. And Jill's speaking later this week. Also, thank you.
Okay, any other questions for Matt? Just gonna scan Slack also. Oh, we got a couple of raised hands. Corentin.
Yeah, well, very nice talk. I do agree with Madikin. You mentioned that we don't have we only have loose bounds with Matplotlib. So in principle, you could imagine doing everything, for example, with D3GS or directly in the browser instead of relying on Matplotlib. Would that be useful, or?
I think it would be useful. We would need to be, so with some of the browser-based visualizations, they mock up image plots using a series of rect objects on SVGs, so little rectangular patches, and that's not always performant. Not all of them do that, and the ones that do, you can usually make them do a different way. But I absolutely think that exploring more browser-based visualization systems and would be very useful. Did I answer your question?
Yeah.
Okay, thank you, Corentin. And Stephanie.
Yeah, so thanks also. It was great. I have a question, and maybe we'll end up talking about this on Slack, but I've never totally understood the difference between how phase plot works and how like projection plot works, because I don't know, they feel really similar to me. You know, you get to choose whatever you want on the axes of phase plot. And I saw you kind of showed both, so I was wondering if you had any answer for that.
Sure. So with a phase plot, typically we do a fixed binning, and you can mock up a projection using a phase plot in unigrid situations. The issue that typically we run into is that phase plots, we're doing a binning operation of infinitesimally small points. So you could also use phase plot for particles as long as the particles have no extent. The issue with a projection plot is that, for instance, coarse cells inside AMR or SPH particles or, octrees, anything like that, they will usually they will usually have extent on more than one cell, or more than one bin in a phase plot. And so that's not generally supported. So the projection plots utilize the spatial extent information, whereas the phase plots are based on the notion that there is no extent. Now, mind you, adding support for extent in phase plots would also allow us to do interesting things with uncertainty and uncertainty visualization. I've never needed that because my simulations are perfect.
Right, of course. Okay, cool, thank you.
Or at least that's what Greg told me.
Thank you again, Matt.
Thank
and
you.